Okay, good afternoon, everyone, and thank you for joining today's seminar from the SBIP seminar series. Professor An Din from Singapore University of Technology and Design, SUTD, will introduce the speaker. So, An, please.
Thank you, Dimitra. Good afternoon, everyone. Welcome to the second SBIP public seminar, and this is my pleasure to be able to introduce Mr. Ruan Pingcheng to give the talk today. Pingcheng is a final year PhD candidate at the database system lab in NUS, and his main thesis work has been centering around looking at blockchain system from the database perspective, and he has won many awards, one of which is ACM Sigma 2020 award. For his another award, which is VLDB Best Paper Award in 2019, and all of this work, I hope he will present today. And without further ado, over to you, Pingcheng. Over to you.
Hi, Anne. Thank you, Anne. Thank you, Dumitro, for your introduction. Now I'm sharing my screen for my presentation. Hi, Anne. Can you hear me and see the share
yes,
screen
we
properly?
can hear you and see the slides. Please go ahead.
Okay, thank you. Hi, everyone. I'm Pingcheng, a PhD candidate under Distinguished Professor Pingcheng. Welcome to our SBIP seminar. Firstly, I would like to say thanks to the chair and to all the audience for giving me such a valuable opportunity to present my PhD research. The title is Blockchains, Novel Data Platforms and Beyond. Through the popularity of Bitcoin and ICO, I believe all audience hear about blockchains, which is the Bitcoin's underpinning technology. We all know about that blockchains are closely related to cryptocurrencies, but few is aware that blockchain technology itself, which shows far-reaching impact on industries as databases did for decades ago. The line of my research is to treat blockchains as the data processing systems, like databases, and perform related optimization and enhancement. In the following presentation, I will firstly motivate this research direction in an introduction, then comes with my literature reviews. Afterwards, I will explain my first research work, Dichotomy and Fusion, which proposes a taxonomy that unifies blockchains and distributed databases. My second work aims to improve on the blockchain utility, which explores to add data provenance to smart contracts. At last, before the conclusion, I will explore to apply the database concurrency control for the performance speed up. And at last, I make the conclusion. Blockchains originate from Bitcoin, which firstly achieved a decentralized payment system. To unleash its potential, Ethereum introduces smart contracts so that users have the flexibility to encode their business logic. However, these two systems are permissionless, such as all members are free to join and leave the peer network. But in enterprise-grade applications, membership are fixed and authenticated. In light of this, system designers take advantage of the permission block assumption and bring forward a number of permission blockchains, such as Hyperledger Fabric and R3 Corda. While security people place emphasis on permissionless cryptocurrency system, our DB people are primarily focusing on contract-based permission ones, as contracts are capable to support arbitrary workload. It makes blockchain more step away from the cryptocurrency purpose and now enter into the data processing domain. This diagram shows a general architecture on the contract-based permission blockchains proposed by the Blockbench in our lab. From the data processing perspective, we divide the permission blockchain into 4 layers. Application layer accepts client requests and propose contract invocation to the consensus. The consensus form the ledger and provide the second transaction to execute. Their effects are persisted in the data model layer so that it can respond to the application query. Again, our vision is to optimize permission contract-based blockchain like a data system. Our optimization sets the following 2 goals. On the one hand, we would enhance the system utility with negligible overhead. On the other hand, we would improve the performance without compromising the security. Notably, we designed to ground all our optimization on a popular permission blockchain, Hyperledger Fabric. Just like security people place their focuses on Ethereum. Here, we present the baseline results in our testbed. On simple YCSP workload, Fabric achieved around 1.5K TPS throughput when block reaches 1K transactions. Fixing this block size and evaluating a more complex small batch workload, the actual throughput decreases drastically due to the excessive transaction abort. And the abort rate increases when we further increase the skewness of the workload. Our baseline result demonstrates that blockchain performance is still far from databases, opening massive opportunity for the optimization. Now, I'm giving a quick summary on the blockchain research frontier, according to the 4 layers as classified by the Blockbench. Based on the data model, a transaction either transaction-based or account-based. The former mostly applies to cryptocurrencies, and the latter for those with contracts. In the former, researchers are primarily focused on the transaction graph analysis on the cryptocurrency flow. It is in order to discover certain transaction pattern. In the latter, due to the Turing completeness of contracts, security people are especially interested at the operation charging plan in the contract, especially in the Ethereum community. This is to defer denial service attack. There are 2 notable execution paradigms. Canonical blockchains adopt order execute pipeline, where transaction execution or validation is a part of the application predicate for the consensus. However, as execution and consensus are coupled together, clients cannot fully anticipate the transaction effects given the execution engine anomaly. This behavior leads to a number of vulnerabilities, attacks, and prevention guidelines and tools. Execute order validate architecture addresses this issue by separating the consensus and the transaction execution into 2 different phases. But as we see in the previous experiment, it does not work well on the scale workload. Well, some research directly tackled this issue to reduce the abort rate. Some others introduce new execution paradigm by relying on more assumptions. Consensus attracts the most interest in blockchain community, and there is a clear distinction. Security people focus on their attention on permissionless one and introduce a variety of proof-of-work analysis, such as selfish mining. There are enhancements such as Ethereum Ghost protocol and variants like proof of space. The attention of distributed computing people is more on the classic Byzantine fault tolerance replication, like PBFT. Interesting, some proposal in order to operate on a permission setting, they elect committees or organize peers into shards in order to apply the state machine replication techniques. At last, some entrepreneurs introduce proof of concepts, prototypes to demonstrate how blockchains could transform the industry. They are from the most preliminary applications which explore blockchains for security commitment ICO platforms to the more established sectors such as financing, banking, supply chain, IoT, healthcare, and so on. From our literature review, there is a clear gap between the research efforts in academia and industry, where researchers pour massive efforts on permissionless cryptocurrency systems. Industry draw vast demands on generic workload support with their permission setting. And this observation motivates the necessity of our research, which is to apply database techniques to improve the contract-based permission blockchains for their better utility and performance. Now we are entering my first work, which unifies blockchain databases. Since the moment a smart contract has transformed blockchains from a cryptocurrency platform into a generic data processing system, its similarity with the conventional database has been under hot discussion. However, the existing works focus on their distinct properties to external applications. For example, many propose a flowchart like this to guide practitioners for their decision. On the other hand, many system designers notice database and blockchain share abundant technical concepts that are similar, from contract to store procedure, from consensus to replication, from cross-chain swap to inter-share transaction. However, we observe all these discussions, though popular, are rather scattered. Our work aims to fill this gap by proposing a unified taxonomy that encompasses systems under a generic distributed transaction platform. But why is that necessary? It serves two purposes. On the one hand, a unified taxonomy helps to explain the performance in a fine-grained manner. For example, Blockbench empirically demonstrates that the blockchain's performance is far from databases in both YCSB and small batch workloads. This conclusion is rather intuitive and misplaced details. For example, what factors account for their magnitude level discrepancy, and why the gap for the small batch shrinks? On the other hand, there are emerging a variety of database blockchain hybrids in academia. By matching their designs into our taxonomy, we can provide a reasonable behavior prediction for future system designers. Our taxonomy consists of 4 independent dimensions, which serve orthogonal purposes and raise corresponding challenges. Replication copies data into replicas and brings challenges on their synchronization. Concurrency aims for more parallelism, but must regulate their interference. Storage trades off between the access efficiency and data verifiability, and sharding partition data for the scalability, but it makes tricky on the cross-shard transaction. In later slides, we will label the performance-favored design in blue and security-favored design in red, so that it is clear to see that databases occupy a position on the performance end of the spectrum. Permissionless blockchain is on the other end, while permission blockchains is in the middle. The replication is further broken down into 3 subdimensions. The replication model deals with the basis to replicate it on. Both types of blockchain replicate transactions due to the presence of ledgers. The database is storage replicated, as replication works upon operation logs. In replication approaches, we differentiate a consensus approach and a primary backup approach. By where there exists a view change mechanism to fail over the leader replica. Apart from the above, we also classify a share lock approach, in which systems outsource the replication task to an external lock producer, such as Kafka. We observe all application approaches exist in distributed databases, and they also exist in permission blockchains. Permissionless blockchains only adopt a consensus-based replication. In terms of the failure model, permissionless blockchain assume for Byzantine behavior, and database only with a crash failure. Note both failure models are observed in permission blockchains, but permissionless blockchains have to additionally mitigate the cyber attacks. In concurrency, permissionless blockchain takes an extreme precaution approach to execute transactions serially based on their ledger sequence. It makes their behavior easy to reason about. Database in the performance favor explore much concurrence as possible as long as not violating the isolation levels. Permission blockchains ride the fence again. Like Fabric, it executes transactions in parallel but commits their effects serially. In terms of storage, all contract-based permissionless blockchains provide a verifiable organization to protect their states. They mostly do it via Merkle tree variants. On the contrary, nowadays the database direction is to optimize the storage by to harness their hardware. We notice some permission blockchain directly utilize the off-the-shelf hardware optimized storage like LevelDB, while some others additionally build a Merkle tree on top for the verifiability. Despite this, all blockchains explicitly maintain a ledger abstraction for the full history, where conventional databases only keep limited history logs for the recovery. Blockchains assign data to shards in a node-aware manner. Security can be reflected that much efforts are dedicated to avoid Byzantine adversary corrupting any shard. In contrast, we observe database dynamically adjust the workload assignment to smooth the bottleneck. Another perspective about how they implement a 2PC for a cross-chart transaction, where databases employ 2PC with a single transaction coordinator. Permission blockchain add another level guarantee by implementing 2PC on the same machine replication. There is no central or entity or group in permissionless blockchains. A cross-chain transaction is separated into multiple decentralized sub-transactions, each to be carried out by participants by their incentives. Based on our taxonomy, we broadly classify all blockchain database hybrids existing in the academia into the following two categories. Out of the blockchain databases provide a database abstraction to the users. Internally, this database is powered by a blockchain. Out of the database, blockchain attempts to implement a decentralized blockchain from the well-established databases. Hence, the former are storage replicated, where the latter's replication is transactional aware. But as we have seen in this red box, in other dimensions, both types of the hybrid system have a mixed preference with respect to their own security performance trade-off. In the experiment, we evaluate the following systems: TiDB to represent a new SQL database, etcd for NoSQL one, Quorum for permission blockchain with conventional order execute paradigm, and Fabric for the EOV execute order validate paradigm. We first apply the YCSB and a small bank for their peak performance. Now we tweak the YCSB workload as shown in this table to differentiate the effects of each taxonomy dimension. On their peaks, we observe that blockchain database gaps are still there, but not as large as that block batch reported. We attributed the key reason is that HStore selected by block batch is an in-memory distributed database with primary backup replication. HStore represents an extreme pointer design space, makes it rather similar and incomparable to blockchains. Moreover, under the skew small back workload, the gap drastically shrinks, notably when switching from uniform simple YCSB to more complex small back. The performance of Fabric degrades and Quorum improves. In later experiments, we managed to account the former due to the workload skewness, while the latter is due to the larger record size. Our major finding on replication is that transaction replication model restricts concurrency, limiting the impact of replication approaches and failure model. These conclusions can be demonstrated by comparing Fabric and TiDB. Fabric's update latency increases when systems are overloaded. It is because blocks pile up in a queue waiting for the sequential validation. In contrast, the quorum's performance remains almost unchanged when switching from crash-tolerant Raft to Byzantine-tolerant IBFT for their consensus. On concurrency, EOV blockchains have low performance under workloads with high contention and constraints compared to the older execute ones, and the workload impact the most on NewSQL databases than NoSQL ones. These can be seen from the following behavior. In blockchains, Fabric throughput decreases when a transaction has get more skewed or a transaction touches more record. Similar pattern can also observe between NewSQL database, TiDB, and NoSQL one, etcd. On storage, we find the ledger abstraction in blockchain incurs significant storage overhead. The overhead needed to guarantee state verifiability is small. This is shown by decomposing storage in Fabric and compare with TiDB. We additionally compare the space assumption of two verifiable data structures, Merkle patriarchal tree in Ethereum and Merkle bucket tree in old version of Fabric, and we observe that the former demands for more space. The performance of sharded blockchains is far behind that of distributed database due to their security requirements on the shard formation and periodic reconfiguration. This conclusion is made from comparing AHL, a sharded blockchain, TiDB and Spanner and Google Cloud, with scale to 48 nodes and reported in this chart. Even though all systems exhibit horizontal scalability, the throughput of AHL is still far behind that of two databases. In the meantime, it further degrades for 30% if we turning on the shard reconfigurations. Periodical shard configuration is to mitigate adaptive adversaries, which are assumed to make use of membership information to infiltrate specific shards. The following diagram proposes simple and a framework for a back-to-the-wall throughput forecast for performant blockchain database hybrid. Drawn from our experimental insights, we position the replication model, whether the storage replication or the transaction replication as a foremost factor. And then it comes with the failure model. We believe that the crash failure tolerance and the Byzantine failure tolerance closer in transaction replicated system in storage replicated system. The chart on the right draws out the predicted range and their reported throughput on write performance. Using the two factors stated above, we can predict the throughput effectively. For instance, Veritas exhibits better throughput than Chainify because it uses storage-based replication and safety protocols, but its performance has a high variance because on the high contention, the throughput can decrease significantly. My second work is fine-grained secure efficient data provenance in blockchains. This work is motivated by our observation on two isolated blockchain usages. On the one hand, the distributed ledger provides a public auditable transaction history so that all stakeholders can validate and inspect the system evolution. This evolution is known as data provenance. On the other hand, smart contracts allow for developers to encode their business logic so that blockchain can serve as a trust-free building platforms. But one fundamental limitation of current smart contract that it can only manipulate on the latest states. Just like these contracts, it can only read the current token balance at the time of the execution and then perform relevant modifications. A natural question arises that can we combine these two uses together such that the data provenance explodes to smart contracts? The benefits are evident. With the provenance-dependent contracts, developers can express more business logics. For example, the above token transfer can be conditioned on the historical balance and the threshold. In the meantime, the contract can still enjoy the blockchain-provided transparency and auditability. One might argue that why not to break the procedure into two steps? We first do the offline analysis in history, computing the historical balances, and then selectively send the transaction based on the result. Well, this practice is securely flawed. It is because the block proposer has the ability to place another token transaction, transaction A, ahead of this transfer transaction B. Transaction A, by manipulating the balances, turn off the triggering condition, which is supposed to be true for the transaction B. But transaction B will still make effects, breaking the intended business logic. Security people refer it as front-running attack. Ending provenance of smart contract comes with the following challenges. In a cryptocurrency-free blockchains, provenance is ambiguous. We need a clear semantics to define a data dependency. In addition, given a well-defined dependency, how can we properly stop them with the verifiability is another concern. And the last, history is accumulating in a pen-only ledger. It requires special care for their query efficiency. For the provenance definition and handler, we partly leave the problem to the contract developers. In the application layer, we require the developer to implement the following proof helper interface along with the contract development. The interface provides the method name, identifier, and value of the access records. We require developer to relate the read record identifier to the write record ones to express their dependency. For example, in a token contract as above, we can simply relate the recipient address to the sender address. Then the semantics of data dependency take in the form of the token flow. The proof helper interface will be triggered by the system with the populated parameters immediately after executing the contract. The captured dependency will be passed for the storage. For the provenance query, we provide the following APIs in order to track the captured dependency and state version. For example, in historical query, we accept a block number to specify a version for state entry that is valid at a block. Apart from the value, it will also return a block number that contains the transaction that updates this version. For example, the state ID can be account number, and then the value will be the historical balance at a specified block snapshot. From the above data model, we know that given a state identifier, such as account identifier, and a version number, we can uniquely determine a state entry, such as the historical account balance. The entry is represented by the circle here. Given this, the verifiable storage for backward dependence is quite straightforward. In a nutshell, we add a layer of abstraction on the Merkle tree in order for a Merkle DAG. Specifically, the leaf entry now additionally contains the cache pointers to these dependent entries. Consequently, the data provenance uniquely determines the Merkle tree root. But this naive approach does not apply to the forward dependency. For example, at the moment when entry SK1V1 is created, we do not know which future entries may depend on it. We tackle this challenge by storing this forward entry hash to the succeeding entry with the same state identifier. For the case of SK1V1, we store its forward entry hashes to SK1V3. Here, we rely on a core property of the previous proof helper. It guarantees that if a state entry is created, the forward dependency for its predecessor entry will be fixed, as no future entries such as SK0V4 will depend on the predecessor like SK1V1. The above works on the dependency storage and query, but how about version query? How can we efficiently locate an entry for its version value given the history is constantly growing? We introduced a blockchain tenure index to address this issue. This index is called Deterministic Append-Only Skip List, DASL. For each state ID, a DASL is built for all their state entries. In DASL, lists of different levels maintain state entries for different versions. Suppose a record has a version number 13510. Its level 2 list will maintain all entries who are the first in their ranges 2, 3, 4, 7, 8, 11, where L3 handle larger ranges and its entries are more sparse. The figure on the right outlines the DASL after version 10, 12, 16 are appended. DASL provides the following benefits. Firstly, it is deterministic, hence it well fits into the Merkle DAG, so that it still maintains the content addressability of the Merkle tree root hash. Secondly, it favors more on recent versions, which better fit for user behavior. This diagram outlines the major instrumentation on original fabric in layers. In application layer, we add the provenance handler for contract developer to reap their benefits. We slightly touch on the execution layer so that proof helper would determine the dependency after the contract invocation. The major changes is on the storage layer, where we completely replace the original storage with fork-based, so that we can, when we're implementing the DAG and the DASL index, we take advantage of the fork-based provenance well self-verifiable and strongly typed features. Our experiment involved the following systems. The original fabric without any provenance support. This is to quantify the extra overhead. Ours is referred to as fabric sharp O. We slightly update the fabric to fabric proof O, which directly dumps the version and dependency information to the storage. The O here denotes for the scheduler, which will be changed in the next work. We reuse YCSB and smallback workload. Due to its simplicity, YCSB allows us to focus on the version storage without concern on the data dependency. This is in contrast with smallback, given our major instrumentation on storage. We deliberately take account for the fine-grained measurements. From our measurement, we haven't observed any remarkable performance drop in terms of the peak performance, where there are some gaps between the fabric proof with fabric when the block is small, as in this yellow box. These slides make the performance drop accountable, but are skipping out. But as we can see, by composing the data provenance NUMA quantum, we can save the efforts to the block scanning for the offline analysis. Now we take out the storage layer for the specific analysis. It is clear that DASL is more favorable to the version query with smaller distance, but the flat storage does not. And DASL managed to flatten the latency distance relationship to the log scale. To evaluate the dependency query, we populate the storage with a DAG that tracks mobile lineage in a simulated supply chain. In the experiment, we measure the latency of a forward query, which is to track the affected mobiles from a defected material, and a BFS backward query to enumerate all materials of a given mobile. From the results, we conclude that our fabric sharp storage can support complex dependency query better than a flat storage in fabric proof. In the last experiment, we populate 100 blocks with YCSB workload. We place our focus solely on fabric sharp to understand the storage constitution for a blockchain application. We observe ledger constantly account for the majority of the storage cost. In particular, blocks occupy around 66% of the entire space. Results further confirm the previous conclusion. In addition, we find that storage consumption for data provenance is far less than expected, as shown in the negligible blue bar. Now we are entering the last work. The last work The title is A Transactional Perspective of Order Execute Blockchains. The novelty of this work is to apply the database techniques for the blockchain speedup. Note that we place specific attention on execute order blockchains, such as Hyperledger Fabric. We apply the well-established transactional theory from databases, especially from optimistic concurrency control, to reason about the blockchain behavior. Unlike the previous work that focuses on storage layer, this layer manipulates on the transaction or execution layer. Our key observation and motivation is that EOV blockchain achieves strong serializability on their transaction level. This is too stringent than the protocol requires serializability. As a consequence, many transactions in the ledger are wrongly aborted. We explore to reorder transactions to reduce these aborts, abiding the serializability instead of the strong serializability. Next, we briefly explain what an optimistic concurrency control transaction is like in databases. Each OCC transaction has at least the following information: a start timestamp, which marks the time where the read records are retrieved. The end timestamp marks the instant when the transaction is about to take full effects. Each transaction also includes the read records and write records. During the commit phase, the database will do the validation with the above information to determine if a transaction is valid according to the isolation level. Isolation level decides on allowable constraints on the inter-transaction interference. The most popular level is serializability, which requires that resulting concurrency effect is equivalent to a serialized transaction schedule. This diagram below shows 6 canonical transaction conflicts in OCC databases. Conflicts are due to the read-write access to the identical record. The first 3 between non-concurrent transactions, and the last 3 between concurrent pairs. Note that among these 6 conflicts, the last anti-rewrite is the only conflict whose conflict order is opposite to their temporary order. According to the conflict serializability theorem, the effect of a serialized transaction schedule is equivalent to any serialized transaction history that respects the conflict order. Note that the dependency query of the serializable transaction schedule must be acyclic. These slides lay out the basic background on EOV blockchain. The transaction lifecycle considers 3 phases. In the first phase, a peer receives the execution request proposal from a client and simulate the execution against the state of a particular block. The simulation returns the key and the version of the read record and the install value of the update record. The peer itself will not possess the simulation effects on their states. The orderer, the client is responsible to assemble the simulation result into a full-fledged transaction and send to orderers. The orderer will agree on a common sequence of transactions and then pending the order transaction until a block formation condition is met. For example, if the number of pending transactions reaches the size limited block, the orderer will batch them into a block and inform peers. At last validation stage, each peer will independently pull 4 blocks from orderers and validate them. For each block, the peer will sequentially validate transactions. During the validation, the peer will check the endorser signature and the version of the read record are still up to date. If so, the peer will install the updated value to the state database. Otherwise, with the stale rate like this, the transaction is getting aborted. As I mentioned above, some in-ledger transactions may not be considered valid and hence get rejected for the serializability. This is due to the previous validation step. This problem is getting prominent with the increasing request skewness as shown in the chart. Worse still, due to an inherent system bottleneck, there is a limit on the max attainable system volume. Even the workload is totally serializable. It again motivates the necessity to reduce the transaction abort to maximize the throughput. We now describe how a transaction in EOV blockchain resembles to a one in OCC databases. We first define blockchain snapshot and snapshot consistency in EOV. A blockchain snapshot is the state after block M, and we define sequence number to a two-value tuple n plus 1 and 0. If there exists a blockchain snapshot for transaction simulation, we say that transaction is snapshot consistent. Borrowing the terms OCC, the start timestamp of this EOV transaction is equivalent to the sequence number of the read blockchain snapshot. The end timestamp is determined by the transaction location in a primary order determined by the consensus. To be specific, the end timestamp is also a two-value tuple, that the first value is the block number, and the second is the transaction position in the block based on the primary order. We adhere to the OCC notation to denote for a EOV transaction, and shown on the right. We inherit the concurrency definition that two transactions are concurrent if their execution interval overlaps. From this visual proof with the marking timestamps, it is easy to see that two transactions in the same block, like transaction 2 and 3, are concurrent, but not vice versa. Note that our goal is to reorder transactions under the less strict serializability instead of the strong serializability. There are differences explained here. The left diagram shows a serializable transaction schedule as their concurrent effects are equivalent to a sequential one. But it is not strong serializable as the equivalent sequence does not conform to their temporal order. Unlike the right diagram, the transaction sequence on the right is exactly ordered by their actual timestamps. We then derive a theorem stating that a transaction schedule without anti-rewrite conflict achieves strong serializability. The crux of the proof is that hinges on the fact that among 6 conflicts, the conflict order of anti-rewrite is the only one that is reversed with the commit order, which is a necessary condition to form a cycle. With this theorem, it immediately follows that Fabric and Fabric++ achieve strong serializability, simply because their stale read version validation prohibits of any anti-rewrite conflicts. As we have discussed previously, the strong serializability is a cause to the excessive transaction abort. We naturally ask, with serializability instead of strong serializability, how to reorder pending transactions before batching them into a block. Under our definition of ordering, we present 2 lemmas, which proofs are well explained in the paper. Reordering does not impact on the commit order and the conflict order of the non-concurrent transaction pairs. A transaction does not change its concurrency relationship with others after reordering. This lemma shed insight that we can only focus on the reordering implementation on concurrent conflicts, as mentioned as demonstrated in the red box of these 3. Next, we can derive a lemma from the diagram that the conflict order preserves between C rewrite anti-rewrite but not C write from these visual diagrams. As we have seen above, among 3 concurrency conflicts, only C rewrite allows us to swap the conflict order by reordering their end timestamp. Based on the above, we can derive the following main theory. A transaction schedule cannot be reordered to be serializable if there exists a cycle with no C rewrite conflicts between pending transactions. This is again demonstrated in these 2 diagrams. From the above theorem on the transaction reorderability, we propose the following abort-free concurrency control, which can abort unreorderable transaction earlier. The entire procedure consists of 3 algorithms. The first is simply to simulate transaction with snapshot consistency. The second is performed once the transaction is primary ordered by the consensus. It computes all conflicts from a transaction graph G without C write with among all pending transaction B. If there exists a cycle, we immediately abort T. Else, we incorporated it to G and added T into the pending transaction set P. When the block formation criterion is met, we topologically sort P with respect to the connectivity in G. The tuple sorted order determines the position each pending transaction in P. G is a singling, hence P is a subgraph of G. Hence, P must have a topological order. No transaction abort here. At last, we restore C write conflict from the order P and incorporate them into G. We now present a security analysis on the reordering, especially under the blockchain Byzantine setting. We assume that safety and liveness holds in the original consensus, and then we investigate how reordering impacts on these two properties. Firstly, the safety holds simply due to the deterministic nature of a reordering procedure. If two honest nodes agree on a common primary order, resulting transaction after reordering are still guaranteed to be identical if both honest nodes follow the exact reordering approach. However, the liveness may be compromised that the malicious peer may bias the primary order to deter certain transactions based on a public transparent reorder logic. The mitigation can be simple. We can simply hide the transaction contents during the consensus and only reveal them for reordering after the primary order has been established. The left diagram demonstrates the instrumentation of the algorithm in original fabric, where the major instrumentation is now on the order processes. Due to the time limitation, I will skip discussion on how to grow our abstract algorithm into concrete implementations. The implementation mostly deal with how to achieve the snapshot consistent simulation, conflict computation, cycle detection, graph representation, and C write transaction conflict restoration. As before, our experiment is designed as below. In the first part, we compare concurrency control method in the original V4 scheduler in fork-based power fabric shop and level DB power fabric probe. YCSB workload aims to understand the reordering overhead when the workload is completely serializable, and smallback is to investigate the speed up as well as the provenance interference. In the second part, we employ more complex workload so that we have greater serializability potential and fine-grained skewness control. Each transaction read and write 10 out of 10K records, among which 10% are hot ones. The access ratio on hot records are adjustable. We will also compare different concurrency control methods, Fabric Shop O with original V4 scheduler, Fabric Shop P with adapted from related work Fabric++, Fabric Shop S and L each migrated with one standard and one latest OCC technique from database, and Fabric Shop is ours. Due to the timing constraint, I will directly show the major findings. In the first part, we have the minimal overhead under contentionless YCSB workload, over 30% speed out on smallback, and with minimum performance interference. In the second experiment, after determining the optimal block size for each baseline, we observed that our Fabric Shop Pro outperformed all the other systems in almost scenarios. And last, in conclusion, this presentation demonstrates a great potential on the system-level optimization on contract-based permission blockchains. We firstly introduced a normal perspective that unifies blockchains and database into a common taxonomy. And then we proposed two optimizations, one for utility and the other for performance. We've grown all our optimization from the original Hyperledger Fabric in Fabric Shop and open source it. Where there are a number of noticeable future works, from the making contracts declarative like a SQL language, or building a centralized lateral verifiable database to employ blockchains with the federated learnings. In the end, we hope our presentation can appeal to more researchers and engineers on our research direction, which is to optimize contract-based permission blockchains from a data system perspective. That's all. Thank you. Hi, now I'm welcoming any questions. And Dumijo, can I return the control to yours?
Yes, sure. Thank you, Pingcheng. So let's take the next 7 minutes for questions. Okay, so I allowed you to unmute. You can ask questions.
Thank you, Pingcheng. Very good talk. Thanks. As I was unable to unmute myself, I just want to ask if anyone in the audience have any question for Pingcheng. Maybe I start first. Can you tell us a little bit more on like what are the following up work that is spawning off from the work? I mean, like not the one that you describe in the future works, but like have you you've been aware of other people's work that is similar to what you did, like from some other groups in the world?
Actually, recently I'm quite interested as the database and blockchain hybrids, because from my perspective that I think blockchain itself provides too much security guarantee. This is far more expected in most applications. And that's why I see some centralized databases they borrow some features and security guarantee from blockchains and still provide some reasonable levels of security. And I believe these databases, I mean the blockchain as SBIP database may suit for most needs and can have more impact in the future. This is the area that I most interested right now.
Can you give some names on some of the
I remember I think last year Sigma there's a blockchain work called FocalDB, which also attempt to combine the blockchain and databases, and notably they add some databases features on top of the blockchains. I'm not clear about the details, but I'm mostly interested about this research direction.
Right. Talking about scalability, right? What about all this like off-chain approach to scalability, to scaling transaction?
I think this is a very wonderful breakthrough that I think the essence of the off-chain approach is to move the computation off the chain and do it offline, where blockchain is to resolve some conflicts or resolve some contention once they have the conflicts. I think security people are mostly focusing on this topic as they are mostly studied the problem from a security perspective. For example, they mostly assuming that clients or participants are rational, and then they have some strong security incentive analysis with respect to their behavior. But for this off-chain approach, I seldom see them in the database literature. I think database people are less interested at the behavior analysis, such as the security, such as the incentive analysis in the security community. Yes, so in all, I think off-chain approach is a very promising direction, but and it is mostly focused in the security community, but not in the DB one.
Okay, great, thanks. Anyone else have other questions for Pingcheng? from the engineering perspective, what would you say the most challenging aspect of blockchain systems are?
Sorry, what do you mean by engineering perspective?
Like from coding, like from programming, from building blockchain system, from the experience.
Oh, from my experience, I think the consensus part, even though consensus is well established in decades, but coding them, especially how to code out a PBFD, is very tricky, and under the Byzantine setting, and even a misimplementation will cause great risk, even in the financial loss. So from the engineering perspective, I feel that the consensus part is the most tricky to code.
I see. Okay. Do you think most of the existing blockchain system are well built?
I have invested some mainstream blockchains such as the Hyperledger Fabric and Quorum. I think mostly they are well built. They have already shown much impacts and attract many community efforts. And the Ethereum used to have some security blocks, but they has all been tackled by the community joining help. That's why I feel definitely are well built with the community efforts.
Great. I think I'm run out of questions. I'm just waiting for other people in the audience to ask. I see some familiar names here, so I think many of us are familiar with what you do.
Yes, thank you. Yeah, yes. Actually, last Friday, I do my thesis proposal is a similar presentation, except that I do not fully expand my third work.
Okay, so if there are no other questions, maybe we can just end here.
Okay.
Oh, wait.
Hello. Can you still hear me?
Yes, I think you can
see. There's a question from the chat panel from Edward. That do you think?
So yeah, I think the question is for you.
Yeah, I'll say the question. Repeat the question. That do you think the fact that we know the IDs participate in a permission blockchain would allow for less strong security? Yes. For this question, I think my answer is yes. Yes, because if we have a fixed authenticated membership, then everything action, and suppose we do any action is attributable or accountable, and then once then we can attribute their behavior and then we have some evidence to account for their misbehavior. Not only me feel that with the permission membership can relax some security, I also see some argument from other community and the corresponding system designs. For example, for example, in Hyperledger Fabric, they allow for the crash failure tolerant raft as a consensus, but correspondingly, they must turn on the TLS security communication. It is because raft is crash failure tolerance. In order to make it work, and they must to use the TLS with the authenticated membership. Hi, Edward. Do you think are you happy about my answer? You can type it in the panel. Okay, thank you.
Thanks, Pingcheng. I think, as Dumi said, if there's nothing else, and I think let's thank you again. And
Thank you.
We appreciate the effort today. Great.
Yeah, thank you
So
very
we can
much.
end here.
Thank you very much, everybody, and have a good day. Bye.
Thanks. Bye.